Hey guys, this is the first video for Unit 7, and this one is about a new topic or a new concept we're going to talk about called work. So to lead into this, let's picture something. Imagine you get a job, and at your job there's a big pile of bricks on the ground. Here's a big pile of bricks. And your boss says, hey, your job is to move those bricks. That's it. All you gotta do is move them. So he comes back 8 hours later, and it looks like this. Well, he's going to say, well, you didn't do your job. You didn't move them. Now, you maybe held them straight up, or you could have wiggled them around and put them right back. But when we talk about work, we mean actually changing or changing a property in something, and really specifically at that. So if I wanted to move these bricks, I'd have to push them. So I need a force. Well, I can push on the bricks and have them not go anywhere, and that doesn't count as work. If I push this board, I'm not doing work because it's not going anywhere. But if I were to say push this marker, I did work. I moved the marker. So we define work really simply. Work is force times distance. Now you might say, well, Mr. Quinn, I thought we didn't use the D word. Well, distance is not a bad word, it's just not the same as displacement. Displacement is a vector quantity. It's not only did you move it a certain distance, but also in a certain direction. Distance is just how much did you move it. So if your boss says your job is to move this pile of bricks 1 meter, and he doesn't specify the direction, it doesn't really matter. You can move it right, you can move it left, you can move it towards us, it doesn't matter. So work, let's write the word work. Work equals force times distance. We could give a unit here. It would be newtons times meters, or Newton meters. That's a little weird. So instead we're going to use this new unit called joules. And we're going to write it as a capital J. And this is really a joule, J-O-U-L-E. And it really means it's equivalent to Newton meters. Newton meters. So there we go, there's work. So let's do a quick sample problem, see if we understand the concept. Instead of having to push a pile of bricks, let's take something that's a little bit more sensible. How about a football sled? So here is a football sled, and coach says, hey, push this thing. And this football sled has a mass of 100 kilograms. And you also happen to know that the sled part of it that sits on the ground is a coefficient of friction of 0.2. If he said push it 20 meters, how much work would you do? Well, let's see. Now I'm not going to do my given list and everything. I'm just using this problem as an example. So if this were a homework problem, we'd start by doing givens, but here they are. The next thing we do is look at formulas, so let's look at this formula. I want to know how much work I need to do, so that'll be my question mark. And work is force times distance. Well, I know my distance, but I'm not sure how much I got to push. I don't know how hard I have to push yet. I'm going to have to push it, I don't know how hard. And I can figure out how hard because the thing I'm pushing against is friction. You know, as I try to move this sled forward, friction is going to be pushing it backward. If this were on, say, an ice skating rink, or if it was on a big giant Teflon pan, I could just kind of push it with a finger. But because it's on grass, it's hard to push. There's friction. Can we figure out how much friction? Well, sure. The force of friction is equal to mu times the normal force. Well, I know mu. I don't know the force of friction. And the normal force, I don't know right off the top of my head, so I'm going to put an X there. Well, what's normal force again? That's the surface pushing back on me. So in this situation, it's this arrow going up. Boy, this diagram's getting messy, isn't it? So let's replace it with a free body diagram. There's the force that I push, and then there's friction going backward. And I know I got to push at least as hard as friction. Then there's normal force holding the sled up. And the reason normal force is there is because gravity is pulling the sled down. So, that means that in this problem, not every problem, but in this problem, normal force is equal and opposite the force of gravity. Well, I also know that gravity, Fg, is equal to mass times acceleration of gravity. Well, I know this, and I know this, so I can get force of gravity. If I can get force of gravity, I can get normal force. If I know normal force, I know friction. And if I know friction, I know work. That's it. Not really complicated. But we'll see this in action a little bit more as we start talking about energy, and in particular potential energy. Bye for now.